Hello. In a previous video, I went through a process in which we could generate an animation like this. What this showed here was a series of binary clocks. So here, for example, we have an 8-bit clock, 1, 2, 3, 4, 5, 6, 7, 8. And what we did is we made an arrow rotate round between 0 and 1 with a frequency of 2 Hz, giving a state change of 1 Hz. And it was a way in which we could represent binary counting. So you see that as the hand ticks round, this number is incremented, and that occurs for all clocks. And what was interesting about this is that the frequency relationship between the clocks were that every clock to the left of the one on the right ticks half as fast. So this one ticks at 2 Hz, this one ticks at 1 Hz, this one ticks at 0.5, 0.25, etc, etc. And in this video, what we're going to do is we're going to be making this so that we can generate some nice movie files of these ticking clocks. But you see, we have a problem. That this animation here, for example, consists of 8 bits, and I'm plotting the arrow going round at 60 FPS. So there are 60 discrete changes of the arrow every 60 seconds on this clock. This one will be 120 changes every revolution, 240, etc, etc. Now the problem with that is that this file itself would generate 15,000 images. So if we were to go ahead and say save, so I've enabled here a block in which the figure is saved. I'll go ahead and play that. So this is an 8-bit clock, so it can only count 256 seconds. And in the folder where I've told it to save, you can see it's generating the files. However, it's very slow. It only generates around 3 to 5 files per second. And so it would actually take a very, very long time to even generate all these files. And 15,000 files is quite a lot. What happens if we went to, say, a 12-bit clock? So a 12-bit clock looks very nice. Ignore these lines, these are just alias and effects. But what you'd see is that for this 12-bit clock, we'd end up having to generate 245,000 image frames. And when I tried to do this, each image frame was around 85 kilobytes. And so when combined, all of these image frames would come to around 20 gigabytes. So you've got 245,000 frames coming to around 20 gigabytes. And when I actually tried doing this, I stopped at around 15,000 frames because I thought it was too much. And ended up putting so much stuff in my recycle bin that my recycle bin wouldn't actually empty. So it was causing all sorts of problems. And so the aim of this video is to do something a bit more clever. So for example, if we look at the clocks again, like when we actually did this in the video, we realized there was a frequency relationship between each of these clocks. Why not do something where we say, maybe just make one clock that ticks round once, and then post-processing, so when we create the video, we can go ahead and make copies of this first clock and just run it at half the speed for every single time we do it on the left. Now, some people watching this might be thinking, well, why don't, instead of just saving to files, you just use the built-in FFmpeg writer as part of Matplotlib? And the answer to that would be that Matplotlib still then has to generate the frame for every single frame in the movie, and that would still take a very long time, but it would have the benefit of not having to create the files. The way we're going to do it is we're going to just create one instance of the clock ticking round once, and then we're going to do something quite clever in FFmpeg in order to make a nice wide movie of it. So the first thing we want to do is we want to go ahead and create just a single clock. So let's create a single clock. And again, in our previous video, we showed how we did this object orientatedly. So changing to a single clock is very simple. We just change the number of clocks to 1, and that's it. Additionally, we'll change the figure size. We'll change the width of the image. So we'll change that to 2 inches. Go ahead and plot that. You see there. We have a nice smooth clock. It runs faster because it's smaller. And then if I open up the image frames folder, you can see it's generated individual images for that single clock going round. It starts here, tick, 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 etc., all the way around until here. So it forms a complete loop. Now for the FFmpeg command. The FFmpeg command is quite interesting. So I'm going to load in a batch file for this instead, because a batch file will be easier to execute because it's quite a lot of commands. So let's go ahead and make a 3-bit movie. And we'll see in a minute why doing this in just batch files might not be the best solution. And certainly for me, I don't know enough batch command syntax in order to make this into a loop or auto-generate this. What I've got here are some just variables that we're going to use. So we're going to set a variable called scale, which will sort out the scaling. So we're basically saying make a nice wide movie. So this is a 2K movie. Got codec, so it has all the codec information that we're going to use to encode our movie. So it's a H.264 codec, so the libx264. And the important parameters, I've tuned it for animation, which means it will do more look ahead. It's a preset very slow, so it'll try and achieve the smallest files. It'll take more time to try and get that file size down. And the CRF 0, so it would be perfect quality. You can even go ahead and add pix format. You can go ahead and add pix format, should you so please. And then we've got two important variables here, FPS in and FPS. So think of this as FPS in and FPS out. So from our script, we know that the FPS that we used to generate this was 60. So 60 FPS we need to read in. And there's 120 frames because the clock goes around once every 120 frames at 60 FPS. That's how it counts. And so the command for this is quite complex. So we need to launch FFmpeg, tell it to overwrite any file that already exists in case we do something wrong. And then we need to say FPS in. It will read the files in at 60 frames a second. So it's basically 2 seconds worth of data that we read in. But again, we've only created 120 frames instead of the however many 200,000 frames that we could have been doing for this. Let's give it the input. So I've saved all the frames in a folder called frames/. It's simply 1 bit, and it is a 0 padded number, so it's padded with up to 6 zeros, added to 6 places long with zeros, all PNGs. And here's where the magic happens. So we need a complex filter. And what we'll be doing here is we'll just be doing 3 bits for now, just to showcase. First thing we need to do is we need to split our stream. So when we do split equals 3, we're telling it to split this input stream, which is the image stream, into 3 different outputs. So we'll call this A1, B1, C1. And then we need to go to a separate chain, and then we need to manipulate A1. So A1 will be the image on the left, so the slowest ticking clock. We need to tell it to loop. Although for this clock on the left, it won't actually loop, it will only ever go around once. But it allows us to just copy and paste some things. So loop equals -1. That will tell it to loop indefinitely. We then need to give it a size. So that's how many frames are actually in the image. How many frames to actually loop. So that's be 120. And then immediately after that, we do a set PTS filter. So this would be 4. That basically means set the presented timestamp of that stream to 4 times the actual timestamp. So it will actually run slower, 4 times slower. Then we set the FPS equal to 60 here. We could move this elsewhere, that's not important. Then we go ahead and copy this for the remaining 2 streams. Then we change A1 to B1, and A2 to B2, etc. Likewise for the C's. And then for the B stream, the PTS needs to be twice, not 4. And then for the C stream, the PTS needs to be 1. That will mean each clock loops around, given by the number of frames, and it's slowed down by the correct amount, which is 2 to the power of where it is. The next filter we need to apply is we need to then horizontally stack these inputs. A2, B2, C2, and then we do the H stack filter. So it's got 3 inputs, and then we do our scale. So scale is easy, we can just do our batch variable scale, and that's the end of our filter. We need to give it a time, so we know it's going to last 8 seconds because it's a 3-bit clock, 2 to the power 3 is 8. Give it our codec. Again, it's just another batch variable. Then we have an output file, so we'll call it 3-bit clock.mp4. Hopefully that works first time. Never say never, it appears to have done. And then in our folder, we end up with a file called 3-bit clock. Go ahead and play it. So it's doing exactly what we want. Each clock is half the speed of the previous clock, looping round, and at the end they should all line up at the exact same moment, which is what we want. But you see, we do have a problem here, so it's a bit janky. So you see this clock here, it actually looks like it's visibly ticking, and the very simple explanation for that is if we go back to our script, is that we only outputted this clock at 60 FPS, and so the actual change when the clock is ticking slow is very noticeable. Easy way to solve that is let's increase that to FPS equals 60 times 16. That should be 1920 in terms of frames, so 1920 frames. We'll just let that tick along. And while we're doing that, what you'll see is in the frames folder now, we're creating more of these frames. And so there's a much smaller increment now between the clock ticks. So that should result in a smoother animation. So that will eventually finish. Let's just clean up, let's just go back to our FFmpeg command. And so now, FPS in, remember it's now this times 16, which is 960. But now our frame repeat is now 1920. Check that's done. That's done. Go ahead and run this now. Wait for it to finish. Again, 3-bit clock. Look how much smoother that is. So we've correctly changed the smoothness of the arrow going round, so I'd be happy with that. But you see, now we have a slight problem in that this was quite a beefly command to implement. Let's see what would happen if we actually had to... Let's see what would happen if we actually had to do, say, an 8-bit movie. So I'll cheat here and just generate the command. But an 8-bit movie would be a command like this. Look at how complicated. So that is ridiculous. That is one chunky command just to get the 8-bit clock. Yeah, so we've got a real problem here. Is that you would want to maybe generate a 5, a 6, a 7, an 8, 9, 10, etc. bit clock. But writing that out is ridiculous and it'll be too prone to errors. I think what I found a really good way to do this is to just abstract this. So we'll take this and all we have to do is create a little Python file. So here is the file. So one line's commented at the minute, but let's have a look what it does. So import system and OS, because we'll be using those. Okay, it then checks if the argument list that it was given is equals 2, because if it's equals 2, it means it was called from the command line. Then it sets the bits equal to the second argument received. So the first argument is typically the file name, the second argument is whatever the argument you give it. Then do a little print statement generating a movie for this number of bits. And then we start to write out the FFmpeg commands. All we've done here is done the FFmpeg commands, but then use f strings to input important pieces. So you see here where it says FFmpeg -y -r in FPS in curly braces. That takes this variable here, which was the input FPS, which was 16 times 60. And if you look at the output command it will give, it will actually replace that with 960. So we're using Python to actually put in these variables as they are. But the advantage of this is that we can then use this bits value that we give it, and then what it will do is automatically generate the FFmpeg commands for that particular bit number. If we go back to our example here, I'll paste that in. You can see it's automatically generated. It's automatically done. For example, a split equals into 8 different streams, all labeled A to H with a 1. And then for each of those individual streams, goes ahead and does the loop, the set PTS, and the FPS. A little word of warning here is that the loop should come before the set PTS, because when I had it the other way around, it was when it got to very, very big loop numbers, the PTS would cause a drift within the loop. It's better to use the loop first. And look, it's automatically as well inserted the correct 2 to the power. So for here, the 128 comes from 2 to the power bits minus I minus 1, where I goes from 0 to 7 in this case. So we're getting the correct slowdown of each video. And again, it does this for all of the different streams. And remember, this is all coming from one set of files in the folder. We're not generating every frame of the resulting video. We've generated every frame of a single clock ticking. And then we're stacking those clocks with different video playback rates together, all the way through until we get to the hstack command, where again, it inputs all the required streams, stacks them with the required input 8, again, another dynamic variable, adds in the correct scale that we said, does the time properly, so 256 seconds for this 8-bit, 2 to the power 8 is 256, does all the other correct commands, and then even has the file name to be right with 8-bit clock. If I go ahead and run that, so what I've done is, if you just run this script as it is, there'll be no sys.argv unless in Spider, for example, I'll show you. You can go to run, configuration per file, and then you can add command line options in here, should you be so inclined. But we'll just do the default bits of, say, 5 here. If I go ahead and run this, and then the very last thing to do in this script is just do os.system, and then we go ahead and run the command, so we can just run FFmpeg string, so it's going to run this command here. Go ahead and run that. You see it's launched FFmpeg successfully, working away in the background. In the folder, you see a file has been created, which is being populated as we speak. So it's up to 22 seconds at the minute. running quite slow, so it's running at 1.48 times speed, and that's because the output video I'm saying is going to be 2K, so 2560 pixels wide, and then adjust the height accordingly. But there we are, it's created it. It's 32 seconds long, and it looks like exactly what we want. It's ticking round. Each clock on the left is half the frequency of the clock on the right. Also successfully counting the binary number. Lasts exactly 32 seconds, and when it gets to the end, you get the nice alignment at the top, which can then repeat as it goes around. That's working really well, and we've never created any more frames than we've needed to. It requires just the 1920 frames. If you wanted now, and because FFmpeg as well is multi-threaded, there's no benefit as well in running. If you wanted to generate, say, a video for 8, 9, 10, 11, 12 bits, there's no point in having to worry about multi-threading that, because FFmpeg is multi-threaded, so you can just do them sequentially, generate movies. You can do that quite easily, so let's do that quickly. So if I shift right click on Windows, open PowerShell window here, it'll give me a PowerShell window. I can type Python, and I can give it the script name, which was generatemovies.py, and then I can give it, say, 4 bits. And you see, it's successfully launched FFmpeg. About 10 seconds in to the video, which you can see down here. It will tell you where it is in the video. It also tells you speed. Go ahead and look at that video just created. You see, we've created our 4-bit clock, which is really, really simple. I would suggest doing something like this. So maybe launch IPython, and then import OS. And then we can do os.system, and then we can call Python, and then we can call our script, which was called generatemovies.py, and then we can give it, say, 4 again. Let's do 3. You see, that also called for FFmpeg. Wait for it to finish. Put it up to 6 seconds, 7, 8. There we are. Again, created our clock successfully. Now what I would recommend doing is something like this. So you can do for I in range. Let's create the 8-bit clock to the 12-bit clock. And then let's do our os.system. Let's go ahead and call Python with the command generatemovies.py, and then with the variable I, making sure that we encase this in an F string. Zoom in for any players at home. Go ahead and run that. There we are. So it's starting now by generating the 8-bit movie, which you can see here. Create a file with 0 kilobytes because it's currently being created. You just watch that go through. The 2 to the power is 256, so once that reaches 256 seconds, that will be completed. So I'll pause the video here and then come back when it's completed. And so it's almost completed now. You see it's up to 3 minutes 54 seconds. So it should stop at 4 minutes 16 seconds, which it did. And then went straight on to creating the next movie. If you look in the folder, you see 8-bit clock is now being generated. 162 megabytes. Remember, it's perfect quality. There's no subsampling or quality reduction in this, so it's a perfect recreation of the original frames. But you see, it's doing exactly what we want. 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, with each clock ticking half as fast as the previous one on the right. If we just scroll through to near the end, we need to make sure that the clocks are still synchronized. And it looks like it's still doing well. So again, if you put the if you put the loop parameter and the set PTS filter the way around, you get issues towards the end. But you see, even at the very end, we maintain our synchronization. It loops straight back around to 0, 0. So we've now created that 8-bit clock. And again, we didn't need to create the tens of thousands of frames needed to make this animation. We only created enough frames to create a single clock. And again, we've just stacked them together. So it kind of shows you just how powerful FFmpeg actually is to be able to do something like this with relatively few commands. The syntax got a bit complicated, but even if you did this in other software, so I know a lot of video editing software actually uses FFmpeg behind the scenes for their rendering. All that's doing is giving you a nice GUI and maybe some equation input, and then it will just be translating it into an FFmpeg command like this. Well, even in Python, when you write with the FFmpeg writer in matplotlib, it's just creating a big long FFmpeg command to output what you've actually got. And so that's working quite nice. And this command shell now, PowerShell, will just work through. So 416, it'll still keep going because it's now 9 bits. So it should last twice as long as that. It's still going. What it'll find is that will just plow through and create 8, 9, 10, 11 bit clocks. so movie files off that. And I think this is quite good because it really does save time. As I said yesterday, I probably spent, I don't know, close to 8 hours in the background just rendering frames for a 12-bit clock, and it just got nowhere. I was nowhere near getting the required amount of frames, and then I ended up clogging up my recycle bin. Recycle bin still won't empty, so I need to figure out how to fix that. Something like 200,000 files in the recycle bin, which is causing me a bit of a problem. But yeah, I hope you found this video interesting. I thought it was just quite nice to see how we can sort of use some tricks of mathematics, I would call them. So we know the clock ticks round once, and then every clock has a fixed relationship. Just translating that into our video encoding software, which was FFmpeg, and then getting that to do basically all the heavy lifting. So these clocks should be done in, well, I'll say in no time. They're currently running at about 2.29 times speed. So if the clock takes, let's say 8 minutes to tick around, the video is going to be ready in just shy of 4. So thank you for watching. I hope you found this interesting. Always look out. I've got many videos on my channel about FFmpeg. They're just some little short 2-minute videos just showing how to do various things. What I could do is do a little one on this, but probably not, because it's very niche application. It's not really a general FFmpeg thing to do, not really a general movie editing thing to actually go and do. But yeah, thanks for watching. Stay tuned.